So we just did our bank account kind of example, and it was pretty weak, right? And it wasn't very biological. So let's try and bring things in the direction of biology, and we're going to pretend we're looking at population growth, right? And we could. I can't help myself, right? I always imagine like sheep or bunny rabbits or something like that. But you can imagine bacteria. You could imagine infected COVID people, right? You could imagine whatever population, bacteria on a plate doesn't kind of matter, right? Um, we can start with something pretty simple, right? And so how we're gonna do this is we're actually gonna start using our R scripts up here. So if you've got RStudio, you're just gonna go File, New R script, and here it is, right? And we're gonna do this because we're going to type in multiple lines, and if we make a mistake, it's gonna be easy to fix. So what are we gonna do? We're gonna start with our population, all right? And our population is going to be a vector that is just one element long, and this is our starting population. How many, are there 10 bunny rabbits? So there's 10 bunny rabbits. This is going to be on like year zero or year one. Um, how many bunny rabbits are? There's 10. All right, cool. We could imagine if you wanted to, this is 10,000. It'd probably make life a bit more accurate. And then we're going to give some other parameters, like what's the birth rate? How many new bunnies are born every year? I should start saying like COVID infected, so it sounds more, you know, topical, but I can't help myself. They're bunnies, right? Birth rate, right? How many new bunnies are born each year? Now, this is not really how many new bunnies are born each year. This birth rate is what is the percentage growth of the population, or to put it another way, per each bunny, how many new bunnies are born? All right, and we're going to say that this is 10%. That's a 0.1. That's nicer, right? So for every bunny each year, zero point 0.1 bunnies are born. All right, and then that's our sort of initial conditions. Those are our parameters. This is our sort of biological variables. Then we're going to have to deal with a little bit of computer stuff. How long are we going to run this simulation for? Um, so we're going to say T max, our maximum time. That was Brad just bothering me about making sure this content was online. Those with quick eyes probably already saw that. T max is equal to 100. So we're going to run this simulation for 100 years. And then we're going to do something. It's going to seem a little strange, but not too bad. We're going to start our for loop, right? So we're going to go for, and what are we going to do, right? So I'm just leaving that blank and we're putting those down there, right? So this is what we're going to do every year. What are we going to put in here? Well, we're basically going to say for every year. Okay, so we might want to say something like for t e, in 1 to t max, all right? And that would be a pretty good start. All right, let's just leave that in, right? Because that conceptually, this is what we're going to do, right? So we're going to say for t in 1 to t max. So we can look at year 1, year 2, year 3, year 4, year 5, okay? And then what are we going to do in here? Well, we're going to apply our rule. How does the population change? And our rule is that the population next year, right, so which is t plus 1, right, is going to be given by the population at year t plus the population at year t times birth rate. I didn't spell that right. Rate. Okay, so population, it's a vector, all right, and we can add on to it by just talking to the next element, right? So at the start, when we make it, the first element is in space 1, right? Now, if we go t, which in the first loop of this is going to be your 1, and then we say t plus 1, well, now it's 2, right? So that's going to put whatever we calculate here on the right-hand side into the second position. Okay, now we calculate something on this right hand side. Let's just forget how we do it. We just calculate something, we put it into position 2, and then we loop around again. Now t is valued 2, so t plus 1 is 3, right? So each time we're talking to the next, we're assigning something to the next element in the list. We're making our list bigger and bigger and bigger, our vector bigger and bigger and bigger, adding something constantly on to the end. And here is a slight sort of weirdness if we think about what happens at the very last time we run this, right? So we're going to go t is 100. So then we go 100 plus 1. So our last element would actually be in the 101st element. So we actually want to just go -1. All right. So that way we actually only fill it up to 100 points. But that's just coding niceties, right? And I just can't help myself. All right. And this should run simple population growth. All right. So each year, the population in the next year is the current population plus this new population, which is the population times the birth rate. Now, how do we run that? Well, we just click this button that says source, that you probably can hardly see, but it's just up at the top of this, and we press enter, and nothing seemed to happen. But I'm pretty sure something did happen. Now, I am sure for a lot of you, something went wrong, right? And that was probably because you like put in a capital R like I tried to. So when I run source, I get error, ineval, object birth rate not found, right? Code errors are unanimously agreed to be some of the most unhelpful messages on the known universe, especially for beginners. But all it's saying is object birth rate not found. It can't find anything called birth rate, and that's because there is nothing called birth rate. It is a lowercase r, right? And if you used a hyphen here, what's it going to say? It's going to say object birth not found, because now it realizes, it thinks we're saying birth minus rate, right? Underscore. All right, we run that, no complaints. What are we going to do? Well, we should just be able to say plot x, which is 1 to Tmax, and our population, right? And there is our graph. Okay, now we had a new function here, this function called plot, right? And I think I've talked to you guys before about something called ggplot, which I'm going to use later, but I'm not going to expect you guys to use for making fancy, beautiful graphs. We don't need to use ggplot a lot of the time. If we can avoid it, we probably don't. And here we get this quick and dirty little graph that shows how the population is changing over time, right? It's not well labeled. Population isn't, it doesn't start with an uppercase. 1 to T max is a terrible axis label. This is supposed to be years, but we see this exponential growth. Okay, exponential growth. A bit boring, right? It's sort of worth having a quick think about exponential growth. This is without doubt exponential growth. We didn't use any exponentials in here at all. These kind of equations are where exponentials came from. We're not going to get into how they're related, but this is indeed exponential growth. They came from solving equations just like this. Now, why did we have exponential growth? Well, because there's no death for one, right? The animals never die. Okay, we have set up this equation, and in this equation, all that happens is every year the population grows by an amount proportional to the current population. So that will always generate exponential growth. All right, so let's try and be more realistic here. Let's have a death rate. All right, so we're going to add a death rate. Death rate, and we're going to say the death rate is equal to 0.05. So 5% of all bunnies die every year. All right, so how are we going to do this? So we are now going to say minus our population at times t times the death rate. Okay, now that's what are we going to see? What are we going to see in this? So we've got a population at the next year is equal to the population at the current year plus the population times the birth rate minus the population times the death rate. Okay, and we're going to go run this, and no complaints. So let's plot 1 to Tmax, comma, population, right? And we press enter. We still get exponential growth. Now, that is annoying. Maybe it's not annoying, right? But it's not very exciting. And why is that? Well, actually, if you do some sort of high school level mathematics, you can see that this equation actually turns out to be population at times t times something, which is birth rate minus death rate. So it's still the same equation we started with, except where the birth rate, instead of having birth rate, we are birth rate minus death rate. So it's essentially just halved the growth rate, hasn't anything else. So this population will still continue to grow exponentially. All right. So, what are we going to do with that? Well, we are going to think that that is a little boring, I think. And instead, we're going to try and do something a bit more interesting. But I think we might save that for the next video.